Good afternoon, everybody. So I'm Jacopo Schieppati, and I will present some of the first results regarding the adhesion of rubber metal interfaces under cyclic loading. So without further ado, what are elastomers? Basically, elastomers are polymers that undergo cross-linking reaction through curing, so through sulfur of peroxide, and these allow or hinder the molecular flow, and so gives the material a hyperelastic behavior after vulcanization. Generally, in structural application, often these materials are coupled with metals, and therefore, how is the couple act on this material, or is performed? So normally, there is a primer applied on the metal surface, and then the rubber is vulcanized directly on top on the metal into a mold and heated up to the vulcanization temperature. And then we have the creation of the vulcanized rubber and this complex interface that allow the adhesion between the rubber and the metal itself. Regarding the adhesion in the rubber industry, normally adhesion is assessed through peel test, which is quite common and to use, especially especially in 90 degree. This is a typical example. What is important, though, is that during the test, for having reliable parameters, during the test, the angle of peeling should be constant to anyway keep under control. Since we wanted adhesion to be the cyclic adhesion, we clearly the angle during cyclic loading cannot maintain constant unless a really complex setup and testing. So to tackle this, we thought about a new different geometry. This geometry is the lab shear. Lab shear is quite common for the evaluation of adhesive strength. And our idea was to replace the adhesive with this rubber instead between the two metal plates. In this way, it's easy to calculate the adhesive strength in a shear mode. Clearly, the load is in this direction, but the rubber, so that the adhesive experience mainly a shear load. Nevertheless, we have some questions after thinking about this geometry. Will it work for our conditions, or rubber metal? Will it be actually a failure? And if yes, how it will look like? Is it cohesive or a really adhesive failure? And what about cyclic loading? And then can we distinguish between different effects and different materials? So for doing this, we produce this kind of specimen. You can see here the geometry that we choose. It's inspired by adhesive standards for adhesives and adapted for the case for manufacturing processing in our for producing these samples with rubber. And how we did a pre-treatment of metal, as usual, the primer application and then molding in between the two plates of the rubber. What about the material? We used carbon steel, and for the rubber, it was a carbon black field nitributadiene rubber. And then we use different adhesives. So the primer, three different ones, an industrial grade, then a water-based one, and a solvent-based one, to see if we can really catch some difference in the adhesive strength in this kind of specimen, with this kind of specimen. The tests were performed with an MTS system. You can see both quasi-static and cyclic loading. At this, especially, I would like to focus on the 5 Hertz that was chosen. All the parameters were chosen after some preliminary test. And we used some spacer in the clamping to maintain the alignment during the testing. And we monitor the temperature with an ER sensor, because 5 Hertz can be already relevant frequency for causing a heat buildup in the elastomers. Then the fracture surface were analyzed with this infinite focus system by Alicona. This provides a 3D picture of an overview of the 3D overview of the fracture surface. And afterwards, when you will see why we choose this one and not a typical microscope. So going to the results, we performed preliminary tests on the industrial grade And this is a quasi-static one, and we see a typical shear, typical loading curve. And basically what happened is that the initiation or the onset of the cohesion, it starts at the maximum of this shear stress, and then the tail is maintained because then the failure, the final failure occurs, and this is the cohesion. I'm not sure why there are these symbols. Maybe it's a problem of compatibility. However, what the fracture surface is. So this is a color map of the fracture surface with the height, so the thickness of the adhesive part, so the rubber part. These are the upper face and the lower surface, and they are specular, of course. But what I want to drive your attention is that in both cases, in the very lower part, we have a really thin remaining layer, while getting to the upper part, we have a thicker and thicker remaining part of the thickness. And of course, this is specular until more or less here we have the counter part of the thickness. Just keep in mind this, and then we move to the cyclic test. So the cyclic test, we did some sort of Euler curve. So we apply different loading level, and then we observe what was going on. And what we got, it was a really good Euler curve line, and with a really good reproducibility in general. And it was actually surprising, because if you ever work with rubbers, it's really complex and they have big scattering normally. And so this is really a good result in terms of statistically for us. Then we observe, of course, the fracture surfaces, and we took just, I show you two examples at the highest load, and we can see quite similar features as before. So really thin layer here and going upper and upper towards the other side. And similarly to the low load, also similar features. So it's really similar to what happened in a quasi-static load. And we had a deeper look in this, and okay, this just further, just to show the temperature increase that during the test is below 5 degrees, so it was not relevant. But we look what happened more into detail during the failure process. So what happens is that during the loading, the adherence of the metals bends slightly, and this creates a peeling stress. This peeling stress tries to go in this direction, so we have not a real full mode 2 failure, but it is a mixed mode 1 and 2. This was known in literature, and in general, the maximums of the stresses are in the end of this, so in the overlapping area here. As you can see, the maximums of both shear stress and peel stress. So what was going on? Generally, in the end of this overlap, both sides, we have the initiation of cracks that are then going towards close to the interface or along the interface. And then afterwards, when we get that the failure is already relevant, then the cracks merge together in the bulk of the system. So we have a failure that is both cohesive and adhesive. Nevertheless, since the initiation or the onset of this crack happens in the adhesive close to the interface, we thought that could be sufficient to distinguish between different adhesive strength. So that's what we did. We checked then the materials, different materials, so with the different adhesive used. And these are the quasi-static tests. And we see that the curves are pretty similar. And also the data set actually are quite similar, even though we can observe some difference already between the industrial one and the other two. Major differences actually can be found when we deal with cyclic loading. In cyclic loading, we clearly see 3 different lines. Of course, when we move to the right, we have a better resistance to adhesion or better adhesion. better adhesion to better resistance to failure, so a better adhesion. And this is also testified by the power law, fitting with the power law according to this standard. And also by considering the confidence interval of 95%, also it's clear that we can even distinguish between the water base and the water base and the soluble base. So in general, this method is giving, of course, not a fully adhesive information. Nevertheless, is able to give at least a ranking between different materials. And so what we can do is then with this method, we could then optimize the material choice. And yeah, that's the idea behind of this process, of this project and this research. So to conclude, we wanted to investigate the dynamic adhesion of these rubber metal composites. To do this, we used lab shear specimen, and we obtained something that is partially adhesive and partially cohesive. Nevertheless, the crack initiation, of course, at the interface, and so the some information or adhesion can be obtained. And moreover, this method is able to provide a ranking, and so can give some information, especially on about the cyclic adhesion properties. Of course, this is really a more technological aspect, so it's good for company partners that can take their different materials, test, and give a ranking and decide what is best for their material. From a scientific point of view, we will need to work more in terms of analysis of the interface, for example, a chemical analysis, see what is the remaining compound on the surface, for example, what is the complex interface that is remaining, and, for example, a better investigation of the thickness of the layer remaining, if it's rubber, and the primer is just the primer, the adhesive before. And moreover, of course, as I mentioned during the presentation, the mold is quite complex and the stress test is pretty complex. So a better understanding of the stress state inside the specimen would be required to have a better understanding. But of course, these are the first steps of this research, and I hope that this could be a study case for somebody else that we could go on and find something. With this, I thank you all for your attention.